Good afternoon, everybody. My name is Gaston, and today what I'm going to be talking about is modeling and simulation of nuclear reactors. And specifically, I'm going to be kind of focusing on one area, which is called multiphysics. And this is really just a small piece of what we do in the Computational Reactor Physics Group, or CRPG, here at MIT. So as a motivating problem here, let's think about trying to predict the failure of nuclear fuel inside of a reactor. So if you're unfamiliar with light water reactor fuel, it looks something like this. You have these long, thin fuel rods, and inside of those rods, you stack up uranium dioxide fuel pellets, a whole bunch of them, in fact, like 300 or more. And then you take a bunch of these, like thousands or tens of thousands of them actually, and bundle them all together, put them inside of your reactor. Fissioning process does this thing, generates a bunch of heat, remove that with water typically, generate electricity, okay? That's a problem for a lot of other people here. What I really want to focus on is the fuel itself and how can we actually come about predicting what happens to the fuel under irradiation inside the reactor. Because if we could actually accurately predict the fuel, it would mean that we could create better fuel. We could create more reliable fuel, more accident-tolerant fuel, safer fuel, more efficient fuel, okay? And one of the things we want to do is try to actually predict fuel failure, all right? Because fuel failure is messy, costly. Nobody wants that, right? And that's when essentially the stuff inside of your fuel rods makes it out somehow, okay? So this is kind of a motivating goal, is can we accurately predict the process of fissioning inside of fuel and the material science and everything going on with the fuel in order to actually be able to better design fuel. The problem is that the process of what happens to fuel is pretty complicated inside of a reactor. And this isn't meant to be funny, but it is to me anyway. This is an actual diagram from Lassman from a journal article in 1980, where he actually sat down and tried to show all the different physics happening inside of a reactor and how they are intercorrelated in order to come up with the ultimate behavior of what happens to fuel. And if you look at some of these bubbles here, I don't know if you can read all of them, but there's things like coolant temperature and power, which kind of makes sense. And then there's other things like densification, fuel stress, creep rate. And what we need to do is try to come up with some software that can actually model all these physics simultaneously and all their interdependencies in order to predict the ultimate behavior of fuel. And in order to do that, I would take these things and kind of classify them in kind of 4 different areas here. So there is neutronics, which is basically the actual distribution of neutrons throughout your reactor. Thermal hydraulics, which is how fluid moves through your reactor. Thermo-mechanics, which is kind of the mechanical and heat conduction response of the fuel and everything else in the reactor. And then tied in with all these is very important material science as well, because the environment inside of a reactor is obviously very harsh. We have irradiation, we have high pressures, we have high temperatures. And so, as we just saw from Cody's talk, lots of material changes happen inside of the reactor. And so what's needed really is to come up with a piece of software that can not only do each one of these things individually, which a lot of people have worked on over the years, but actually do all of these things simultaneously, all right? And resolve all the interdependencies between them. And that is a thing that we call multiphysics. So in multiphysics simulation, what we're trying to do is actually resolve all these different physical phenomena and all the linkages between them. And we're going to do that by essentially solving multiple sets of equations simultaneously and feeding their results back and forth between each other. You can see that over here on the right. This is kind of a toy problem of heat conduction and solid mechanics. We're solving a set of partial differential equations here for a heat conduction solve in order to get a temperature. And then we're taking that and passing it over into a solid mechanics solve and looking at kind of the thermal response of that material to this temperature field, right? In this case, just thermal expansion here. And then we would actually pass that back and forth and maybe go back and forth here. And there's a lot of different ways you can actually go about achieving a multiphysics simulation, okay? But the basic problem is that we saw that huge bubble diagram of, I don't know, however many, 30 different bubbles or whatever, right? And so you don't really want to just pass back and forth between all 30 of those bubbles. It's not really going to work out. So you really need to take a more sophisticated approach at developing your software so that you can actually solve for all these different physics and resolve all the interdependencies. And that brings us to a piece of software that I started about 8 years ago at Idaho National Laboratory called MOOSE. It stands for Multiphysics Object-Oriented Simulation Environment. And the basic plan is that it's a finite element multiphysics framework that allows scientists and engineers to plug in all of their equations, all their partial differential equations, all their ODEs, and then MOOSE, hopefully with any luck, will go off and kind of solve that system of equations for you and give you back kind of the multiphysics response of your system, all right? And we've used this a lot over the last 8 years to do a lot of different things. You can see things up here like geomechanics, reactors transport. So it's being used in lots of different areas, but obviously our main focus has been on reactor simulation, using it for nuclear engineering. And this is all open source and freely available, so feel free to go to mooseframework.org, check it out, join the community. It's a very vibrant, active community, so go check that out. And that brings me to a list of collaborators because, as Cody mentioned, I mean, we can't get anything done in nuclear engineering without a lot of collaborators. And all the results I'm getting ready to show you, all of these people played a role in that. I don't have time to go through the full list, but I do want to point out my advisors, Ben Forget and Cord Smith, who do run the computational reactor physics group here at MIT. And then, of course, always the ultimate enabler down here, Richard Martineau, who, if you don't know him, you should, but he's my boss at INL. Okay. So let's go back for a second to that puzzle, that set of puzzle pieces that I was talking about, and kind of look at each one individually. So the first one is going to be thermomechanics. And the basic idea here is that we have just a combination of heat conduction and solid mechanics with a bunch of other kind of phenomenon thrown in. And really, this is going to be the primary thing that's going to govern the gross behavior of the fuel, the engineering structural behavior of the fuel. And some of the important behavior here is going to be thermal expansion, densification, which actually there's extra porosity in the fuel and it's under high temperature, high pressure, and so it's actually going to shrink just a little bit or resist thermal expansion some. After irradiation, there's swelling, like Cody was talking about. You build up voids and everything inside the material, and it actually swells and moves. And then there's also pellet cladding interaction. So you have these pellets, as you can see over here on the right, that are moving around inside of their tube, inside of the cladding. Eventually they swell out and actually run into that metal tube, and there's a really complex process there. So this movie I'm showing over here on the right is a simulation from a MOOSE-based application that is built for simulating nuclear fuel. This is a full 3D simulation with every single fuel pellet inside of a fuel rod discretized. So these are the kind of high-fidelity multiphysics simulations that we're looking for that can give us that predictive behavior so that we can actually try to predict when fuel would fail and try to design better fuel. Okay? So our next puzzle piece that we need to look at is the thermal hydraulics. And basically, this is just everything about the coolant and fluid flow through your reactor, all right? And often, we kind of get away with using 1D models here, although there's a lot of research here at MIT on doing much more complicated 3D full computational fluid dynamics here, which is ultimately needed for predictive capability. And I want to point out that the fluid in your reactor can be many different things depending on your reactor design, all right? So we're not only just talking about water here, not only just steam, but other things like molten salt, lead, et cetera, okay? So you need to be able to model that flow through your reactor, the uptake of heat from the fuel, and ultimately your electricity generation cycle. And this movie that I'm showing here is just a simple toy test of another MOOSE-based code called Relapse 7. That's just showing kind of an oscillator here of a two-phase fluid simulation, just a really simple toy problem. The next piece of our puzzle was neutronics, and this is obviously really important. It's how you actually solve for the neutron distribution in your reactor, both where they are and how much energy they have. And this is what's going to ultimately give you actually the power in your reactor and the heat generation rate. And it turns out there's lots of different ways to solve for this neutron distribution, including Monte Carlo methods, There are methods that are called SN and PN. I don't really want to get into what they mean. I'm just kind of listing them out here. But then method of characteristics, but really the workhorse still in industry is still this guy down here, diffusion. Okay? And it turns out that that's really not very good, but it's what is ultimately used everywhere. And so a lot of our job in the computational reactor physics group is developing these more complicated methods and making them usable and fast and efficient. And to that end, here at MIT, we do develop a lot of codes, including OpenMC, which is Monte Carlo, OpenMOC, which is a method of characteristics code, PinSpec, which is a slowing down code. We have lots of different codes within the CRPG. And then ultimately, this code down here that I've developed called Mockingbird that I'm going to talk a little bit more about in a moment. Now, this movie that I'm showing here is a benchmark result from another Moose-based application that's just showing a prompt supercritical reactor transient, basically, where the reactor comes up to power, and you can see the power here. But then there's a coupled temperature simulation going on as well. And as the temperature of the fuel comes up, you can actually see the depression in power here. And so this is showing just how interlinked these different physics are. The temperature of the fuel directly impacts the neutronics, and obviously the neutronics is driving the temperature of the fuel. So it's a very complicated nonlinear system that you need to solve. So moving on to Mockingbird. Mockingbird is a new tool that I've developed here at MIT. It's an unstructured mesh method of characteristics code, which probably doesn't mean much to you. But the unstructured mesh part means that it's very generally capable of solving in lots of different geometries. So we can look at things like next generation reactors, for instance, and test reactors and things like that. And it directly couples to any other Moose fields. So we can solve for heat conduction, we can solve for fluid flow, and we can pick that up and actually have it impact the neutronics directly. And then it's also very massively parallel, so we can solve really large, full-core 3D systems. Okay? And this movie that I'm showing you over here is actually showing a solution scheme of coupled temperature and neutronics here. And you can see the neutronics kind of go crazy for a moment. And what that is this is an all-new way of solving Boltzmann transport that was developed by John Tram over here within the computational reactor physics group. This is brand new stuff as of last year. It's called the random ray method, and it's just getting published now, so you're kind of getting a sneak preview of this. But it's a really cool new way of solving this neutronics problem. All right, so let's put all these pieces together. We've got neutronics, thermomechanics, and thermal hydraulics. So the way this is going to work, we're going to have neutronics feed our thermomechanics fission source. That's pretty obvious, so that we can get our heat source. And then coming from the thermomechanics, we're going to get back fuel temperature, which is going to impact our neutronics solve. Neutronics is also going to just feed the total power down to the thermal hydraulics. Right now there's lots of different choices here. This is going to impact our coolant temperature and our coolant density. And that coolant density is going to head back to the neutronics, which is going to impact, again, the neutronics very heavily, as you'll see here in a minute. And then these two here are linked through a boundary condition. The outside of the fuel basically needs a temperature from the coolant, from the water that's flowing over it, okay? And so here's a simulation that uses all those pieces. So we have our neutronics, we have our heat conduction, and we have our coolant flow here. And this is one assembly, so it's a 17 by 17 set of fuel pins. And these over here look kind of funky because I've sliced them in half and kind of stretched them out so that you can actually see what's going on, okay? But the assembly actually looks like this. And this is just a 48-hour power ramp, just a straight linear power ramp from 0 power to full power. And what you're going to see is the neutronics come up to power, the fuel temperature is going to come up, and the moderator temperature will also start to rise as we start to start the reactor up here. And maybe? Are you got a range? No. Is it going to work? Yes. Okay. So our fuel temperature starts to come up, our moderator temperature starts to come up, and then if you watch very closely, especially watch right over here, you'll be able to see that as the coolant temperature rises, especially in the top of the reactor, you'll get a depression in the neutronics up here, which will actually shift the peak flux down towards the bottom of the reactor. It's a thing we call axial offset. It happens in real reactors. And that's just a hallmark of actually seeing all the interdependencies here between all these physics. So we're actually solving for all three of these pieces of this multiphysics puzzle together here in one code at one time, all right? This is going to allow us to actually create predictive simulation. I do want to point out that Mockingbird is very massively parallel. This is a plot going from 8 processors out to over 13,000 processors on a cluster. And it's doing very, very well. The blue line is Mockingbird, by the way. The green line is, well, it's some BS. But it's a bulk synchronous ray tracing method. But the blue line is Mockingbird. We're doing really, really well. So if you're interested in massively parallel computing, the CRPG is one of the places where you can get that done here at MIT, because we develop massively parallel codes. All right, the last thing I'm going to leave you with is basically our end goal here. And this is a movie from a demonstration I did a few years ago where I linked together several moose-based applications in order to model a full AP1000 core, all 40,000 fuel rods inside of it over multiple fuel cycles. And what you'll be able to see actually is the reactor come up to power, and then, so this is kind of thermal expansion, and then there's kind of this densification phase. And then ultimately, as we keep the power on in the reactor, you'll start to get fuel swelling here. And then it'll go through a reactor shutdown cycle. We'll shuffle around the fuel like we do in real life. And then we'll restart the reactor. We put a little bit of new fuel here in the middle as well. So this was really just a toy problem to demonstrate that we can actually solve, in a simplified form, neutronics, thermal hydraulics, and a full model for every single fuel pin inside of a reactor, all right? Now, this is still very far away from actually being predictive at this point, and that's where we kind of end with all the open challenges, because there's still so much work to do here. But it's very, very exciting that at this point we can start to link together all these tools and actually look toward a future where we can actually have predictive reactor simulation. Okay, thanks. Oh, yeah, I have to answer questions.
Thank you.
Yeah, what's up? Cody was first.
So your second to last bullet, what do you need from me to be able to make science-based predictive material?
I'm hoping you and Mike can actually do that yourselves, actually. But
like related to that, you had 4 puzzle pieces at the end, and
yeah,
then you dropped the materials.
I did, but no, that's a time. That's completely a time thing. That's just totally a time thing. If you give me another 30 minutes, I'll do material science as well, because Mike and I have done a ton of work on linking material science actually into that full reactor calculation, in fact. So, I mean, things that we need from the experimental side are obviously just all the parameters that need to flow into the material science simulations that we do. So we can also do microstructure calculations. We have moose-based applications for doing microstructure evolution calculations to actually evolve the voids around and grow and coalesce voids and interstitials and all that stuff. And then actually do kind of numerical experiments live while the simulation is running in order to feed back up material properties like thermal conductivity, Young's modulus, et cetera. But all that is really highly dependent on the kind of experimental work that you're doing at kind of the microstructure level. Yeah. Miriam, yeah.
All these methods were developed with an application in mind, so predictive fuel damage. Are these methods in the future going to be used for other predictions in the reactor?
Yeah, absolutely. I didn't mean to focus too much. That was just a motivating thing. Really, we want to simulate the entire reactor. It goes out from here. There's moose-based applications doing seismic and everything else. And so we really want to link all the way from maybe multiple miles around a reactor all the way down to the microstructure and do that full system. So it's not meant just for fuel simulation. That was just to kind of motivate us a little bit. Yeah.
Yeah, thinking about Fukushima.
Uh-huh.
So talk about fuel failure. You have a good example in Fukushima. What can you do in terms of predicting things that will future occurrence of Fukushima will be avoided with regard to safety now?
Right. So I mean, there's a big effort right now in DOE in developing accident-tolerant fuels, right? And a lot of that is motivated by what happened at Fukushima. And so one of the things we can do with this framework is we can take a lot of the work that's going on in accident-tolerant fuels and actually try it out inside of our computational framework first, and maybe help narrow down the types of experiments that need to be done. Ultimately, you're still going to have to cook and look a little bit, as Cody put. But you might be able to use predictive simulation in order to help narrow down the number of things you need to cook, or only cook the most viable options, for instance. Yeah.
What I'm thinking of is, when you can do these things faster and faster with massive parallel,
Mm-hmm.
you could do some, for instance, when you're thinking about the future of reactor safety, you can play all kinds of scenarios where you can get quick answers,
Yes.
scoping answers.
Mm-hmm. Absolutely.
It seems to me that should be very, very helpful.
Yeah, absolutely. Agree.
Matthew?
I was wondering, where's the largest gap in this list?
Okay. Yeah, I think, wow, there's gaps everywhere. So, but I got to say, I mean, the area I work in, I guess I'll point it out. The top one is really a huge gap for us. Because actually being able to do high fidelity 3D neutronics is actually still wishful thinking in a lot of ways. I mean, we use the biggest supercomputers in the world in order to simulate one state point of one reactor, all right? And so getting that down and getting it into an efficient package where it can actually be used day to day for reactor design is actually still a huge, huge gap. Yeah.
One last question.
Yes, so I feel that you have like a very complete package of like physics, as you mentioned. You have like material science and mechanics, fluid dynamics, neutronics. It seems to me that, you know, my concern is how confident are you that your solutions are, you know, correct or realistic?
Yeah, absolutely.
You know, have you done any sensitivity analysis or something?
Yeah.
It seems to me that, you know, you have so many packages of physics, and you know, just a very, I feel like maybe just a very small perturbation on, you know, on a temperature, on a surface, you know, that can create some neutronics or some swelling or something that can, you know, not linearly like interact other packages of physics, and so you know, completely give an erroneous or a different solution. Like, do you have like benchmarking with other codes or like with experiments or?
All of the above. I mean, verification validation is always an ongoing thing anytime you're developing a code. So for instance, the Bison code that I showed that was solving that full 3D fuel rod, I mean, we've run hundreds of cases of, you know, comparing to experiments, and then we compare to other codes and lots of different things. So each of the individual packages are typically validated within themselves. Getting experimental studies that have some of the integral effects in a way can be really challenging. And so there are some benchmark problems, and we do run those, like the Neutronics power pulse that I was showing is actually a benchmark problem. It's the LRA benchmark, and so it's a coupled heat conduction Neutronics benchmark. And so we can run that with our code and see if we get out the correct answer. And so it's a combination of numerical benchmarks, comparing to experiments, and we are always actively, you know, actually looking at new experiments and helping to design new experiments to test out the codes. So it's an ongoing exercise all the time.
Let's thank Derek again.